Hello everyone and welcome to my video. This video is going to be an introductory video on basically large language models, fine-tuning, all that stuff using Hugging Face transformers. We're going to do sentiment analysis of financial news data using a data set I got from Alpha Vantage. And I'll have another video which will show you guys how to get that data set, or you can contact me. Let's get started. Okay. So before we get started, I just want to say I'm using Google Colab because not all of you have a GPU. So the important thing to do before you start is you do runtime, change runtime type, and then you write GPU, T for GPU. Note that since the AI boom, getting GPUs is extremely hard. So it'll kick you off after a certain amount of time, the free version. Anyways, let's get started. Okay, so and of course, if you enjoy my videos, please like and subscribe. It gives me a lot of smiles and that sort of thing. And also, this is a pure standalone to NLP. You don't need knowledge of finance, but of course in finance it's very important because you have crazy things like Reuters has some crazy article that Tesla stops Model 2 production. Tesla goes down 6% in a second. Elon says that's a lie. So anyways, it also connects to my big picture channel. But anyways, let's get started. Okay, so the typical large language model process really has a few steps, and I have this link of a video by Andre Karpathy, who's probably the best at explaining these things. He has Let's Build GPT from Scratch, so I think that's a good resource if you guys want to learn more. So basically what you usually have is some sort of pre-trained model. So the pre-trained model usually have some sort of pre-trained model, and then you fine-tune the model on your specific data set. So a normal, an example of a pre-trained model for ChatGPT would be training on the whole internet, basically, right? It's a large generic data set. You train on the entire internet. You don't focus on specific tasks. And the pre-training ends up giving you some sort of document completer, right? And then after, and that's with a crap load of data with a tons of GPU, that's a compute nightmare. So much compute needed for that. But then there's a fine-tuning process because the previous process of pre-training is just basically you basically taught a sentence completer that knows how to complete sentences but doesn't really know how to do anything really meaningful. So then you have this fine-tuning step, which comes after you pre-train your model with the big massive data to get all the structure and the language. Then you fine-tune on a small specific data set. So basically, for ChatGPT, it's the whole question-answer data set. It's a very small data set of question answers. And that data set, that refining, and you can use a much smaller data set for this. And this really refines the model, and it makes it really, really good. In our specific case, we actually want sentiment analysis. So we're going to have, our task will be a classification of bearish, bullish, or neutral, right? And just we're not going to cover this, but a small tiny note is ChatGPT. They actually have a third step, with it's called reinforcement learning from human feedback, which basically means they give the user a few different types of responses. The user suggests what's best, and they optimize a reward function to constantly give feedback and complete and keep improving the model. Okay, so one more thing to introduce is a library called Hugging Face, or a company called Hugging Face. So they write their mission statement: "We are on a mission to democratize good machine learning one commit at a time." So they have thousands or maybe millions of models that people publish there. They have a model hub, open source models, people's personal fine-tuning models. So let's say you can go to the model hub. By the way, as a side note, they have also NLP, computer vision, audio, a lot of other applications. But let's just check their model hub for a second. So you have all these models of people that fine-tuned and trained. You have metas like llama model, that sort of thing. So like I can search LLAMA, that's Meta's llama model. For our purposes, we're gonna use this thing called Finbert. So there are actually two big Finberts. There's the original one from Process AI, and then if you search by most downloads, you'll see that Yang has one with 2.12 million downloads. So that's going to be the model we're going to use. So basically, this is okay. Sorry, and this model is built on the BERT model. I'll explain it in a second. So yeah, so you can search by like most used and that sort of thing. So let me explain it in a second. So okay, so but basically, Hugging Face in general has like a ton of these models. They also have tools for all the fine tuning process and using the models and that sort of thing. Remember, I talked about like fine tuning and stuff like that. Doing it on your own is really hard. A lot of times, like you have a neural network, you have to remove the last layer. You have to then set up all your optimizers, all your gradients, all that good stuff with like PyTorch. They have like a trainer class that lets you do that for you. So they make all these things like very user friendly and very easy to use. Like all the steps of applying the model as is, B, fine tuning, C, they give you everything out of the box, deploying the model. Also, they have support for many languages and that sort of thing. Okay, so let's talk about the model we're going to use to fine tune. So the model we're going to be used to fine tune is actually called Finbert, as I mentioned above, and we're going to use the last one, which is the Yang's version. So BERT, if you guys are not familiar, was basically a revolutionary type model by Google, and it like basically revolutionized things in NLP, captured relationships in text, and had state of the art performance at that time. Like now, of course, there's models that are a lot better, but at that time it had state of the art performance. After a famous paper called "Attention is All You Need," when they introduced the transformer architecture, which really revolutionized large language models, because the transformer model, as opposed to like things like recurrent neural networks and LSTMs, could be massively parallelized and trained in a much better way on modern parallelizable GPUs. I don't want to get into too much details, but basically, like the BERT model was one of the first like state of the art ones. In the BERT model specifically, pre-training, there are two main tasks. One is like called masked language modeling, where you randomly, like, let's say in this sentence where I explain this masked language model, you randomly like remove some words, and then you try to predict those masked removed words. And then there's also next sentence prediction. I don't want to get into too much detail, but that's how they pre-train the model. And then for specific applications, people will fine-tune the model. For Finbert, they actually continued this pre-training step by training on a giant corpus of financial data from Reuters TRC2. And then they fine-tune it to a small, tiny data set of 4,500 sentences of various news articles in financial terms from something called Financial Phrase Bank. And you had like all these experts annotate, so it was really high quality data. And then later, Yang had a data set of 10,000 manually annotated positive, negative, neutral sentences from analyst reports. So he or she further fine-tuned the model, and the performance got a lot better. Although in my experience, the performance of the this Finbert, the Yang one and the original one, are roughly the same. Maybe this one does better on all classes. But anyways, oh, by the way, he also has a pre-trained one. He recommends for pre-training. But okay, I don't want to get into too much details. But anyways, this is going to be the base model we're going to use. I'm going to show you how to use the model as is. And then I'm going to show you guys how to fine tune and improve it to the sentiment analysis task. Okay, so basically that's the goal of this video. Is first I'm going to just show you like how to get a model from Hugging Face and basically make predictions on that model using the pipeline. And then I'm going to show you how to fine tune that model to your specific data set. So just I wasn't explaining it so well. The transformers library from Hugging Face has a pipeline module which basically simplifies everything. You just give it a sentence and it outputs like whatever you want to predict. In our case, a sentiment score. So let's first talk for a second about some preliminaries. You really need a GPU for this. It takes forever without a GPU. I'm going to now show you some libraries you need to install. Most of these libraries that I'm using are already installed, but there are a few that you need. So pip install, I wrote upgrade, accelerate, and datasets. Accelerate is needed for the trainer model, which is for fine tuning. So let me run this for a second. You actually need to restart after you install this because the accelerate needs you to restart. Not everything needs you to restart, but accelerate needs you to restart. Okay, so once this is installed, then we're gonna import libraries. Okay, we're gonna need Torch because we're gonna use PyTorch. So we're gonna have import Torch. We're gonna need NumPy and Pandas. It's always good to have. And then we're gonna want some of these from scikit-learn to evaluate our model. We're gonna want train. First of all, we're gonna want train test. I actually don't use train test splits, so let me get rid of that. We're gonna want balanced accuracy score and accuracy score. I mean, maybe not the best metrics, but it's a way to measure performance. But now, what we really want from Hugging Face, so maybe I'll write this as like PyTorch deep learning NumPy, and I'll post this notebook after. And now we want the transformer stuff. So okay, so these two below are for transformers. So I'll write hugging face transformer libraries, and this is Hugging Face data sets. They have their own data set type. Okay, so the install worked. Now I do runtime, restart session. Make sure you have a GPU. Again, runtime, manage, change runtime type, GPU. You have to restart after you install. Let's do the imports. Okay. And, okay, let's do the imports. And now, after they load up, we're going to check if a GPU is available. So, like, I'm going to just copy the command that's usually given everywhere basically with PyTorch is to check if a GPU is available. You do torch.cuda that is available, and then you set it to 0 if it's available. But we have one GPU, so set it to 0. Otherwise, -1. With multiple GPUs, I'll try to actually make a video on that, but it does cost money. So yeah. So yeah. So you set it says CUDA available. GPU will be used for computation. And the device is set to 0. Okay, so now we're going to load this Alpha Vantage dataset I was talking about. And again, you can contact me on getting the dataset, but I'll have a video that explains it. So I do this Alpha Vantage dataset. It says it'll delete it after the runtime expires, which is annoying. But basically, when you get disconnected or you disconnect, it'll delete it. So anyways, it's loading the data set to the file system, and then we read it in with pandas, and I'll do .head so you can see it. It's still loading, so in the meantime, I'll do .head. And let me show you guys how this looks. See, we have to wait until it gets fully blue. I think it's, there we go. Oh, not yet. I guess it has to be more than fully blue. Okay, see. So this is how the data set looks. There's a title. We should be using the title in our sentiment analysis, but to make this video be a little bit smoother, I'm not using it, or faster. And then there's like URL, time published, author's summary, Tesla CEO has pushed the so they had a thing where they had like many tickers. It had like ticker sentiment. It had like Tesla, Rivian, and that sort of thing. In the pre-processing, I'll show you in the other notebook, I removed cases where they talk about multiple tickers. I only kept one ticker, and I took that specific ticker sentiment. So it would be either somewhat bearish, neutral, bearish, somewhat bullish, bullish. But like since the model, the Finbert model was optimized for just negative, neutral, and positive, I then switched the labels to negative, neutral, and positive. So negative is anything bearish, somewhat bearish, or regular bearish, and bullish, anything bullish, like somewhat bullish and bullish, will be positive. But you can also like fine tune to now 5 labels if you really want. I'll show you how to do that. Basically, you have to change the last layers, how the last layer works. Okay, so one more small thing now is like our summary is the text field we want to use, but for determining the sentiment. But because the trainer assumes like the default for optimizing like a BERT related pre-trained model is it needs to be called text for some buggy reason. So let's just recall summary text. So I'll do this with a rename. I'll do df.rename summary text access equals 1, in place equals true. This just renames summary to text. We can look at the label distribution, by the way, if you're interested in it. Like you can do value counts, and as you see, this is the original sentiment label, and this is the sentiment label. Maybe I'll do normalize equals true. That gives you the ratios. So you see you have 44% neutral. For the positive, you'll see it's about 37% if you add the somewhat bullish and the bullish, and the negative is actually a small amount. So this has a big class imbalance. So keep that in mind. Which is weird because it seems like every single article against Tesla is bearish. So I would question their scoring system, their sentiment analysis. But of course, I took data from like 2000. Let's see where I took data from. I took data df. I have this. Sorry, it's so funny when you're running it on Colab. It takes a long time sometimes. Time published. Published. .min. So I took data from 2022, 2024. I guess they had a period here where there was positive. I also have a graph over time in my other video of the data set, how the sentiment gets more bearish over time. But I think this is weird. Like this data set is really weird. It's not like this in real life. It's way more bearish. Anyways, okay. So so first of all, let's talk about inference and NLP. So inference is basically kind of like making an answer. So like in ChatGPT, it'd be like basically giving you an answer to your question, right? For our case, it'll be classify sentiment, right? So there's a few ways you can do it. You can do it manually. So what is the manual version? This is a step-by-step version of using the model directly. Let's show you how to do that. So basically you load the model and you load the tokenizer, and then you basically tokenize your text and then apply the model, and then you change the model's numeric answer to a word answer. So I'll explain that. So let me just say it again real quick. So Hugging Face has like this transformer API that has a pipeline, which basically you can do like something like pipeline text classification is your task, and then you can do dot predict. Basically, you can call it on your sentence, and it'll automatically give you the sentiment, right? But we're going to show you like manually the process that needs to be done. So if you guys are not familiar, by the way, tokenization is like you have text and you need to like split it up into chunks, into little pieces. So like so you can think about it mostly as words. So the inference would be one token, in will be a token, NLP will be a token, this colon is a token, language models, all these are tokens, right? And then at the end, this period is a token, and then you can have like an end of sentence token. You can also have an end of starts token. Basically, it's usually words, but then there's more sophisticated models that are like character level or byte level, which is like a combination of the two. But think about it as words for now. Those are the tokens, and then those get converted into like numeric numbers, so you can like do it in models. But I don't want to talk about tokenizing. If you guys are interested in that, leave a comment and I'll make videos on it. But okay, so the first approach is a manual approach of predicting sentiment directly using the model and tokenizer without using a pipeline. So first things first is we need to get the model from the model hub, right? So how are we going to get the model from the model hub? Well, first we specify the model's name. So this is the model's name. The model's name is like, so I go here. This is the model's name. This thingy. This thing is the model's name. And then I'm going to load the model. So how do you load the model? Since our task is sequence classification, it's auto model for sequence classification. That from pre-trained. I know it's kind of ugly, but that's how it is. And then model name, and then I wrote to the device, so you can put the model on the GPU, because you're going to need it later for that. And then we load the tokenizer also, which is the same path as the model name. So auto tokenizer from pre-trained, model name. I guess you can have a separate token path if you really wanted. So we load that up. Okay, and the first time it needs to download the model. By the way, this is a very small model. If we were to download like Llama 70 billion parameters or Meta's model, this would take forever. Anyways, so first thing we should look at there's like a config to the model. So if I do model.config, it'll give us like more information about the model. So if I do model.config, you see I get like all this information like attention dropout probability, classifier dropout, all these things like layer norm, all these things, and also label to ID. So like this is how it labels it. So negative is 2, neutral is 0, positive is 1. There's also the reverse. There's like ID to label 0, 1, 2 for neutral, positive, and negative. There's hidden size. There's a lot of other things. Vocab size. A lot of interesting things here. Pad token. ID. Padding is like when you have like a sentence that's not long enough, you pad it, you like add zeros to it, so everything will be the same. There's all these like number of attention heads, number of hidden layers. You really need to know the paper. It's called the paper is called Attention is All You Need. It's like the most famous paper on transformers. This is like the revolution of this whole like large language models thing. Anyways, so this is the paper. I'll put it here. Is all you. I hate Colab. I mean, I like Colab, but like. Sometimes it's different than Jupyter. This is Transformer Revolution. or maybe I should say AI revolution. And then I'll put the link. It's hard to understand this, so don't feel bad if you don't understand it after even 30 times. Okay, anyways, later we're gonna need the ID to label, so I'll just write this like ID to label here. ID to label. Okay, so let me show you guys the process. So the process is, let's say we start with a sentence, right? So let's say the market outlook is very positive thanks to new economic policies, right? So the first step is we want to convert the sentence into tokens. So we use this tokenizer thing, and we do inputs equals tokenizer, sentence, return tensors means equals PT means we use PyTorch, padding equals true means we pad a sentence to like, let's say our length is 512 for our model, and we have 200, we add padding, so a bunch of zeros. Truncation equals true means if we have more than 512, we truncate to 512, and max length is the 512. Okay, and so this is the tokenizer, and then you actually want the tokenizer to be on the inputs to be on your GPU. So this is how inputs looks by itself after the tokenizer, but like these are not on the GPU by default. So you have to do this. You have to make sure that they're all on the GPU. So you iterate through them, and you need the value these values to go to the GPU. By the way, the tokens like it's an abstract thing. Like before, I spoke about tokens as words, but really like you can have a few things as tokens. So that's why you have like these input IDs. These are like the tokens, and then you have masks and stuff like that. But anyways, this moves it to the GPU, the dot device, and now we have to use PyTorch to make predictions on the input tokens. I want to say some models started with TensorFlow, so you use TensorFlow to make predictions, but this model's base was a PyTorch version of BERT, so it's like PyTorch is like the natural version. So basically with Torch, it has a little bit of ugly syntax. With torch.nograd, outputs equals model, star inputs, and then you get outputs. And look, you get a basically the score, you get the logits, and then you have to take an argmax to find basically the prediction, right? So we're going to do that. So because I'm using np.argmax, I need to first move the logits to the CPU from the GPU, and then to NumPy. And then I do access equals 1, because if this was a list, it was many of these vectors, I would do it across the row and not the column. So now I get the predictions. I get just 1, and then I have to map these predictions to basically like what they mean. Is it positive, neutral, or negative? And one really annoying note is that the two Finbert models, the original one and this one, have different mappings, and that tripped me up for a long time. So basically, just to get the value, we get like, I just wrote mapped array. I use this ID to label we defined above here, and then whenever it's 0, you make it neutral. Whenever it's 1, you make it positive. Whenever it's 2, you make it negative. So now, oh, I just ran that. You get this. You get positive. Okay. So this was like the manual approach of doing it step by step yourself. But basically, Transformer from Hugging Face has a pipeline which does every damn thing for you. All this like auto tokenizing and performing the inference, doing the argmax, and then like getting the label name. It does that for it. And I wrote a note, make sure you specify the device, because you do not want it on the CPU because it takes forever. So let's show you how to do that. So 2 ways you can do that. Number 1 is you can just specify the model name as we did above from the model hub. So like instead of loading the model with the model name, you can just put it straight in the pipeline. So you can do pipeline. Let me write everything down. Task equals sentiment analysis, model equals model name, batch size, and device. Device is very important to make a GPU because if you do inference on a lot of things, it's a difference between taking like an hour or 1 minute or even seconds. So now you can do the same thing as above, all these crazy steps in just one line. Sentiment pipeline, the sentence, you get positive, same as above. Okay, and you could, by the way, just as a side note, you can also create this pipeline by specifying the model and the tokenizer, not just the model name. So you can do something like sentiment pipeline equals pipeline. Still task is sentiment analysis, model equals model now. Tokenizer equals tokenizer, bad size, and so on. But here just model equals the actual model, and tokenizer equals tokenizer, and here it's model name. And then so now you can make the prediction, of course, and you get a positive prediction. Okay, so now I just want to show you guys, like, if we make a prediction on the entire data set, just to see how the model performs out of the box. Okay, so let's do that for a second. So we want to remember our column that we renamed from summary to text is what we want to predict on. I'm going to predict on this column. You know what? Actually, before I do this, maybe let me just show you guys something for a second. So I had this sentence is very positive. We can try a few other sentences just to give you an example. Market outlook is very positive thanks to new economic policies. So that's good that it's positive, but just to show you how the thing works, because it's not perfect, is very negative. Negative is okay, it gives you negative. But then once I do this, it's interesting. It's very neutral. It also gives you negative. I thought that was funny. So the neutral is not great always. Maybe if I just do market outlook is neutral. It's still negative. Market outlook is unknown, neutral. It's not perfect. It's not the best model, okay? It's just FYI. Okay, but let's just try to see if we can fine tune it and make it better. So we want to remember, we want to make predictions on our on this column, text. I wrote to-list. Okay, so this is what we want to make columns predictions on. So we can just do like something like this. We can do preds equals sentiment pipeline of this whole thing, sentence at a time. You get preds, and this is going to give us a list of predictions. So now the difference here is now I have a list of these texts, and for each text I get a prediction. It'll give me a label and a score, like of what probability that was. So let me show you how it looks once it's done running. So I'll just show you the first like maybe 20 predictions. And this is where it's really important to make sure you use the GPU, because it takes a lot longer without a GPU. It seems like I use the GPU. Okay, so just to show you the first 20 predictions, you see you have label and the score, that sort of thing. So if we just want the prediction name, we can extract that out. So we would want like something like this. We can list comprehend through this, and we get pred for pred and preds, pred label, and I'm gonna set that to the data frames prediction column. And then let's check how the model is doing. Let's do a group by. Let's do original sentiment label text and prediction. And this is where it's interesting. Like, okay, as you see, the somewhat bullish, you still are pretty good. You do more positive than negative, but you mess up with a lot of neutral, which is okay, because I guess somewhat bullish could be like neutral. And somewhat bearish, for example, is very different behavior. You actually do a lot better, it seems, and you don't have as many neutrals. So I guess there's a distribution shift. Hopefully what we're gonna do next with fine tuning will help with this. The neutral seems pretty good. And then bearish itself, you have a lot more negative than positive, which is good. And bullish, you have a lot more positive than negative, but you still have a lot of neutral. So I guess, remember when I said it seemed like the distribution over said bullish. But anyways, we're going to fine tune and see if it improves it. If we just want to look at the labels itself without the specific somewhats, you can do this. And you see it's a little bit, see, for negative, you do a lot more negative right than positive, but you do a lot of neutral. For positive, you do more positive than negative. So this is good because like neutral is not the end of the world to mess up on, but just FYI. Okay, so now, oh, sorry. So now, remember above I loaded two different metrics. I loaded accuracy and balanced accuracy from scikit-learn. So balanced accuracy measures like accuracy and you balance it, you like weight it by the class weights. So I think this might be a little bit better for application. So we can do balanced accuracy score, df sentiment label text, and df prediction. And then I get this balanced accuracy score. Oops, sorry. Sentiment, is this how you spell it? Prediction I called with a small p, right? Okay, and then just for the sake of it, you can do accuracy score. This is the non-balanced. Okay, so now we're gonna get to fine-tuning really soon. So just FYI, for fine-tuning, we need the indices and not the label text. So we don't need this text of negative, neutral, positive. We actually want 0, 1, 2. But remember, we have to make sure we get the 0, 1, 2 correct. And that was in the, remember it was in the model.config label to ID, I think. Yeah, so we're gonna now do this. We're gonna do df label equals df sentiment label text dot apply L, and for each one we're going to do model.config label to ID of L. So we're going to switch it to the 0, 1, 2, and it has to be called label for some reason because that's how the BERT trainer later expects it. So now we can just check the value counts. We can do dot value counts. And you see it's the classes are kind of imbalanced. There's a lot less negative, which is really weird. Anyways, let's split our data because we need train test val to show, because overfitting when we fine tune it will be cheating. So we're the Yi Yang's paper in this GitHub I shared above. They actually do a stratified. They talk about, okay, so they have Finbert and they have a fine-tuned notebook. They actually do a stratified k-fold, stratified sample where you get like the same proportion of positive, negative, and neutral examples. Let me show you guys where that is. Here. They do like a train test split with stratified. I think that's not correct. I mean, that's not correct in our specific case. In their specific case, it could be perfect. But in our specific case, just because like around the same time, different news outlets and people talk about like the same topic. So you're going to have things like so close to each other. So if you randomly train test split, you'll have like 5 people talking about the same Tesla not doing Model 2 anymore, and they're going to be very similar to each other. So I'm going to instead do a split across time where I make the first 60% as train, the next 20% as val, and the next 20% as test. But note that the class balances can change over time, so you have to just keep that in mind. But like I still think it's more statistically better than the random train test split just randomly. And so when I split it, I take the first 60% by doing df.shape 0, it's the size, the number of rows in the data frame times 60%, and then 80% of it would be the val endpoint. So the train endpoint would be until the train endpoint. The val would be from the train to the val, and test would be val endpoint, and so on. As you see, you'll get like this is your train size, almost 5,000, and your val and test would be almost a third of 5,000. Okay, so first, before we do any fine tuning, let's just test the accuracy on the test set just to get like some idea. The balanced accuracy, so it's the same thing as above. We apply the pipeline to the text of the test set, and then we extract the label from it, and then we get the balanced accuracy score. And let's also add the accuracy score for fun. So we get those two. Okay, so now this is kind of like before fine-tuning what the score is. So we're going to fine-tune now using the trainer class from Hugging Face. If this is interesting to you guys, I'll make a much more deep dive video on the trainer class, but let's just kind of get started. First thing you need to do is you need to convert to Hugging Face datasets, because that's the trainer needs those. So it's very easy from pandas. You do like dataset train dataset from pandas, and then you give it the thing. So I did it for train, val, and test. And then you need to tokenize the dataset. Okay, so this is where like you want to tokenize it like in a certain way. So you do like so you map these datasets, and you apply the tokenizer on the text, and then you give it like the max length, the padding, and that sort of thing. I don't want to get into too much detail on this. If this interests you guys, please make comments, and I will actually talk about this in length because it's very interesting. And then you need this following line for PyTorch. So basically, all this does in big picture is you make your pandas dataset into the Hugging Face dataset, where you can use it in the trainer object to fine tune your model. And then as the last step is usually it's best to shuffle your training set. So I'm going to shuffle the training set. So I do data train.shuffle. It's funny, in all the examples I see seed equals 42, and I guess I ChatGPT'd it, and it's like some inside joke. Like 42 is like the knowing all or whatever. I don't know. So like now you get a shuffle data set, and then the data set val and test are just like basically validation and test set versions, but in Hugging Face format. Okay, so now that we have that, we have to define the trainer to fine tune our model. So first of all, we want to specify compute metrics. These are like metrics we want to see and evaluate the model based on what's the best. So what it does is you have like this eval prediction, and that's predictions and the labels, and then based on that, like you return like some scores you want to see. So I use balanced accuracy and accuracy. So how you do that is you give a valpred predictions and labels that has predictions and labels. Then to get the actual predictions, of course, from like a probability or a logit to actual number, you do argmax. Then you get the 0, 1, 2, and then we do the balanced accuracy score and the accuracy score. Let's not get into too much detail. If you're interested, I'll make a deep dive video into this stuff. Please write a comment. So now we have to specify the training arguments for the trainer, and then we specify the trainer itself. Just to rush through it for a second, like this is the output directory is where we want to like save the checkpoints along the way. We have all these like things on like logging steps, how often to log, number of epochs, weight decay. This is like a regularization. Learning rate, of course, is very important. Batch size for training and evaluation. So now we specify the trainer. We give it our base model, the arguments, We define here the training data set, which was our data train shuffled, the evaluation data set, and the compute matrix we did above. And then this defines the trainer class. And now let's train the model, right? And the hope is that this does better than the model before we fine-tuned. So remember, before we fine-tuned, we had these things. I'm running it for 3 epochs. Epochs is like one pass through the data. And we'll see how it goes. This might take, it's not going to take that long because it's only 3 epochs. So in the meantime, I'll talk a little bit. I feel like I'm talking too much, but anyways, once this is done, you can actually save the model locally. And you can also upload the model to the model hub. And then once you save the model to the model hub, you can have your own model. So like, as a funny example, while this is running, if I go to the model hub, I have this like useless model I trained once. I think I call myself ML for algo trading. ML for algo trading. So I have this useless model. It's on the model hub. So like you can actually upload to the model hub, and we'll make another video on uploading to the model hub if you're interested. We'll also make videos on how to use like much bigger models like Meta's Llama 2 with 70 billion parameters, and how to use that in fine-tune. Even though that's like not specifically designed for classification, that's more designed for text generation and prompt answering. We'll show you how to fine-tune it for classification and sentiment analysis. So yeah, you can fast forward a little bit of this video, and maybe I'll add timestamps because this is boring if you want. But yeah, this is a training process. Oh, I guess it's the 3rd done. Okay, I only did 3 epochs. Okay, so yeah. Okay, so the balance accuracy is 0.415. This is on the validation set. We actually only did it on the test set. So it's worse already. But like we did, this is on the test set. Remember, this is on validation set. So let's just wait for the 2 more. Okay, but once this trainer thing is done, once it's done training, you can use, it has a method called trainer.predict, and that gives you predictions. So you can do like trainer dot predict, and it gives you predictions. You know what? Maybe I'll spare you guys the details of this and just show you guys how it was in my other notebook when I ran it. So basically, I ran it a few times, and you'll see the trainer.predict gives you the predictions. It gives you like the logits, and it also gives you like a label ID for the label predictions, and it gives you the metrics. Like so like the test balance accuracy was 0.4654. So 0.4654 is a little bit higher than this, so we were able to beat it, and also the accuracy itself the accuracy itself was 0.483, so I was able to beat that. Let's see if we get this. Oh, it's funny. As I was, yeah. So let's see if we're able to beat it again. So it does beat it when you fine tune. There's one more epoch left. Okay. Okay. So let me just say, like, once it's done, you can also like get a pipeline out of it, like we showed. You can either do that by saving the model locally or uploading it to the model hub, and then using it as a pipeline. Let me show you how to do it locally. So you give it like a model path. Sorry, I mean, I should fast forward this and give it to you guys, but like, anyways. So let's save the model as a model path. This is saving it locally. You have to do trainer.model that's saved pre-trained. And then you also have to save the tokenizer, because the tokenizer needs to be in the model path. I didn't change the tokenizer, so And then you have this, okay. And once you save this, then you can load it as a normal pipeline with a new model path, with your new model path, and then you can just use it as we used it before. We can do like preds equals trained pipeline of the sentences, the text, and then we get the predictions. And then we can, of course, calculate the balanced accuracy and accuracy scores as before. So I'll do that, and then hopefully it'll finish running in a second, and then we can compare the results. So let's just add accuracy score just for completeness. Okay. This should finish any second. Sorry it's taking so long. So yeah, I went through the training. Now it's doing the validation. Give us another validation thing. As you see, like, it's good behavior. The training loss goes down. The validation loss goes down. The accuracies go up. And I thought this is done. It is done. So like I said, you can do trainer.predict to get the predictions. Anyways, if you enjoyed this video, if it was helpful, please like and subscribe. Please make comments of what you want to see. If you hate these videos and you want me to stick to my old videos, let me know. Like I said, these are the predictions. You can get the test balanced accuracy 0.441. I guess this might be worse. I guess we got worse in this case. But anyways, you can, like I said, you can save the model locally or to the hub, and then you can make it as a pipeline. You can make predictions, and then you can get scores on those predictions. Anyways, I hope you guys enjoyed this video.